Welcome back, everybody, and welcome to the second half of the semester. And I obviously hope you had a great spring break. And it's been a great pleasure as well to read the midterm answers. I hope it didn't interfere too much with your break. So what we wanted to do today, and also for the rest of this week, is to look at the harmonic oscillations and try to wrap up this part. We are going to have homeworks, this one and the next one, which will deal with harmonic oscillations. And we will not have this topic on the second midterm, which we will dedicate more to two-body problems and many-body problems, and in particular, studies of astronomical systems like the solar system. But it may pop up again on the final. And just to remind you a little bit, the final one is going to be like the two midterms, except that we will have a little bit shorter time. So it will be a kind of take-home exam. And you can look at examples from previous years on what it looks like. It shouldn't be too difficult. So the topic today is to wrap up a little bit about these driven oscillations and go through the mathematics. So there's going to be a formal part and then an analysis part where we look at the results and try to interpret what they actually mean. And we are going to link this up again with codes and do simulations and see what the results look like. And if they agree with the kind of intuition which we get from the equations. There's another thing I wanted to point out for you, and that is some technicalities related to the exercise this week. So you have a shorter time window. By the way, homework 7 is also available. So I try to put them out roughly 10, 12 days before you have to hand them in. Now, this time, due to spring break, I didn't want to interfere with spring break and also the fact that you were struggling with a midterm. So we have a shorter time window, but again, we are flexible with deadlines. The homework this time, I mean, the first exercise is actually you summarizing what you've done till now. So that's a very useful exercise, actually, when we are halfway in the semester to do that. The second exercise deals with harmonic oscillations. And there is also a short survey, which we would very much appreciate if you could fill in. It gives also an additional score of 10 points. And that's more to see whether we are on the right track, whether things we are doing are a little bit too difficult or too easy, etc., etc. So feel free to look at that survey. It's in the exercise for this week. And we always appreciate if you could just fill it in. For the exercises this week, concerning the first exercise, if we go into that one, so let me just bring up the exercise itself, which you can find if you go into the doc folder or you go into the other folders where we have the display of all the projects and exercises and homeworks, etc. So if you go into homework 6 and you go to the PDF version, for instance, so what you will see is that there is an exercise here where you're simply asked to make a summary of what we have done till now. And there's a way to get started. And then there's one about conservative forces, which is a kind of follow-up. There is a famous potential, which is widely used in simulations of systems of, let's say, interacting atoms, where you take away all the quantum mechanics and you have an effective potential. This is a potential which is called the Lennard-Jones potential, and it's widely used in simulations of materials, for instance. And then there is the next part, which is simply deals with an object in harmonic oscillator potential. So many of these things here follow up a little bit of what you did in the midterm as well. Now, for these exercises, what we would recommend is actually to take a look back at what we did in week 6. And in week 6, that's the week of February 6 and 10, there is a figure which Julie Butler made. And I would just recommend to take a look at that one again. So this is the figure where you have all these relations between energies, forces, acceleration, velocities, and the way we solve equations, etc., etc. So just take a look again at that figure, which goes back to week 6, February 6 to 10. So what I want to do now is to go back to the harmonic oscillations and these driven oscillations. So I'm going to jump into the whiteboard and I will just sit in my corner here. Next time, perhaps you would like to come a little bit closer because my laptop doesn't link with a wireless setup. So I actually have to be hooked on a cable. So perhaps you'd like to come a little bit closer next time. I'm not that intimidating, I hope not. Okay, guys. So let me switch over to the whiteboard and try to look a little bit at the topic today. So we're going to go through some formalism first. And the formalism deals simply with us reminding ourselves about driven oscillations. So this is the equation which we are going to look at. So I'm going to just remind you of some of the solutions which we saw before the spring break. And it's pretty common to apply an external force. This could be a driven force which runs like a cosine. It's a periodic one. It doesn't need to be a cosine. It could be a sine, or it could be a square well signal, as we call them. It could be a triangular signal, and so on. And we will see a little bit later how we can actually approximate these by using Fourier's theorem, where we can actually, if we have a periodic signal, that can be approximated with cosine and sine functions, which makes it extremely useful when we're going to solve these type of differential equations. Because we saw that that differential equation, the first one, goes like a cosine sine multiplied with some exponential decay. And then we can add this external force. And that external force, if we have a periodic force, can always be represented in terms of cosines and sines. That means that we have a particular solution which will be dominated by the frequency of the force which we apply. And after some time, depending on the frequency of the force, then the system will oscillate according to the way we've set up this external force. And that's a very typical situation which you will encounter in many, many applications. I mean, from the car industry to studies of damped motion and underdamped critical motion, et cetera, et cetera. So there are tons of applications of this type of problems, not only in basic science, but also in applied science, in industry, et cetera. So let's go back to the whiteboard and remind ourselves a little bit about some of the technicalities and formalism here. So I'm going to switch back to the whiteboard. Now, feel free to ask questions in the meantime. So let's switch here. So the session today is going to be a little bit formal. And so we need this formalism before we dive into the analysis of the equations which we have. So let's just call this the formal part. So we have the formalism. And by the way, Taylor's textbook is actually excellent in the discussion of these topics. So what we have is a differential equation of this type here, of d of x of dt plus b of dx dt. So this is a damping factor, which is velocity dependent. We don't need to have a linear term. We can have a nonlinear term. And then we have an external force, which we now just choose to be a cosine. And this is as an omega times t. And this omega is normally called the driving frequency. What we did before spring break, when we analyzed this equation, was to introduce a natural frequency where we divide out the mass. We defined a parameter, which is often called a damping parameter. We're going to redefine it a little bit later, which is given by 2 of m times this omega 0. And then we introduced a new parameter, which we call omega tilde, which is simply the driving frequency in the force divided by the natural frequency of the system. And it's normal to call this a natural frequency because it's given by the parameters of the system, which in our case is given by the force with a spring constant k and the mass of the object, which is moving according to this force. So, and then what we did was to introduce a dimensionless time, which was simply given by omega times t. And when we did that, we could then rewrite the equations So I'm also going to introduce this quantity here, which is given by the previous constant. So F0 is just an amplitude of the external force divided by the mass divided by omega squared. So if we do that, we could rewrite the equation, which now has dimensionality length only, plus 2 times this gamma. And then we had a d of x of d tau plus x. And this was simply given by this term f tilde, f0 tilde multiplied with cosine. And then we have an omega tilde times this dimensionless time. So all the arguments to a function like a cosine are always dimensionless. And what we said before spring break is that this solution here, when f0 is different, f tilde is different from 0, then we have a particular solution and a general solution. And the solution itself goes like x of tau, and that's given by some constant times cosine, and then omega tilde times tau minus another constant delta, which we're going to define now. So this is normally called the particular solution, xp of tau. And then we have the general solution when the force is equal to 0. And that was given by some constant C1 of E. And then we have this variable R1 times tau plus a C2 of E of R2 times tau. And this R2 is given in terms of the parameters gamma. And these terms R1 and R2 would lead to a under critical damping, where we would have a cosine sign multiplied with an exponential decay. We could have a critical damping case where we simply had an exponential term multiplied with x, with r. And then x. And then we had the overcritical damping, which is simply an exponential damping, which means then that this R2 is a real number. And in the case of undercritical damping, this R2 has a real number plus an imaginary part. And the imaginary part was the one which gave rise to a sine and cosine for the oscillatory motion. So what we are going to do today is simply to look at the particular solution. And this is going to be the solution which will dominate the system after some time. But that depends on the ratio between the driving frequency omega and the natural frequency omega 0. So clearly, if this applied frequency is very, very small, then the system will barely feel the external applied force. And we will see that from the equations when we start analyzing the results. But what I want to do now is actually to show you how you can get this specific solution. So we are going to guess on the solution because the external force goes like a cosine. So you can always guess on such a solution. And that's a pretty standard approach in setting up the differential equations. And that's the path which you typically follow in this type of physics courses. So normally we don't expect you to set up the mathematics of differential equations and solve them, but we will normally guess on a solution which sounds reasonable, and then we plug it into the equations and see if that fulfills the equations. That's a standard procedure which we will follow here. In some cases, we will solve the equations like you will see next week when we begin with two-body problems. But let's look at the solutions here and how we can actually reach it. So this leads to some algebra here. So we're making a guess on the particular solution. So our guess on x of p of tau is now given by this d, this constant, times cosine. So what we are going to do now is just to plug it in back into the equations. So we have a d times a cosine, and then we have this omega times tau minus delta here. So let's see that this actually gives us a solution to the problem. So when we then plug it back, so plug it back into the equation, into the differential equation, the diff equation, what we get then is the following. So we need then to take the differential equation, which we now have rewritten in terms of a second derivative with respect to this dimensionless time, plus 2 times gamma times dx d tau plus x, and this is equal to f tilde of cosine of omega of t tau. So this is the force, this is tau here. This is the force which we have applied to the system. And then we plug it in, and if we do that, we get, obviously, the second derivative is going to give us a constant d, and then I get a minus omega squared, and then I have a cosine, but now I get a cosine square. It's not a cosine squared, a cosine, sorry. This is the second derivative, and this is given by omega tilde minus this term delta. So I'm just plugging in the equations, and then I get minus 2 times gamma. This is the first derivative, and that obviously gives, so this should be omega tilde, and omega multiplied with sine of omega of tau minus delta. And then I have a final term, which is x, which is simply now cosine of omega tilde of tau minus delta. And then the end of the parenthesis, and this is equal to this f 0 tilde multiplied with cosine of omega of tau. So the only thing I did now was actually to place this back into the equation. So this is a pretty common strategy when you want to demonstrate that this is a solution to the problem. Now, what we're going to do now is to use some trigonometric equations. So everything which we are dealing with now are just manipulations of this equation. And there are some tricks which you will actually see being applied to other physics topics, like when you go to quantum mechanics or electromagnetism, you will see this trick being applied again. So let me just show you the kind of approach which is normally done. So you will now, if you look at this equation here, you can rewrite sine. If you use the standard trigonometric relations, we have a sine plus alpha, now alpha plus minus beta, which then can be written out as a sine of alpha multiplied with a cosine of beta. And then we have plus minus, and then we have a sine beta and a cosine alpha. So this is one of these standard trigonometric relations which we often use to manipulate equations. And there's more to come actually. And this is then given in terms of a cosine alpha, and then you have a cosine beta, and then you have a minus plus, and then you get a sine alpha and a sine of beta. So what we're going to do now is simply to say that alpha is given by this W times tau, and this parameter beta is given by this delta here. And then we're simply going to plug in and use this trigonometric relation and rewrite the equation in terms of sines and cosines. And then the thing is that sines and cosines, they are orthogonal to each other. So we can actually separate the sine and the cosine solution in order for this to be a solution. So that's a pretty standard trick which is used in this type of equations here. So what I'm doing now is simply to take the sine and the cosine, so this omega tilde times tau minus delta, and rewrite that equation within the curly brackets here. So what I get then, when I rewrite it, I'm going to get one term with sine and one with cosine. So I'm going to get a d multiplied with, and I'm going to get a minus omega tilde, and then I'm going to get a cosine delta, and then I have a plus 2 times gamma, and this omega tilde times sine of delta, and then I have a plus a cosine of delta multiplied with a cosine of omega tilde times tau. And then I get a sine term, which comes in addition. So I get a plus, and then I have a minus omega squared tilde over sine of delta. And then I have a minus 2 times gamma, And I have to be careful with the signs because I have I'm using the trigonometric relations for the sines and cosines. So I get a cosine delta plus a sine delta, and this is multiplied with a sine of omega of tau, and then end of curly bracket. And this is equal to this F0 times a cosine of omega of tau. So in order for these equations to hold at all times, then sine and cosines have to, the sine and cosine parts have to equal each other. And you can show this also using the orthogonality of cosines and cosines, or cosines and sines. So in order for this to hold at all times, then the sine and cosine parts have to be equal. So what that means, and this is a standard trick which is often used to isolate terms and equations. So if we look at the term which now has a cosine omega tilde, this part here and that part here, they have to equal each other. So we can actually divide out cosine omega tilde times tau, and then we can take the sine part by itself. So what we get then are two equations. So one, we get an equation where we have d multiplied with minus omega squared of cosine delta plus 2 gamma of omega tilde of sine of delta. And this has a plus cosine of delta. And this is going to be equal this term F0. And the second equation which we get is the one which relates to the sines. And then we get, and I'm dividing away with d. So we assume that d is different from 0 because we have a driving force. So we get a sine delta, and then we have a minus 2 gamma of omega of cosine of delta, and plus a sine of delta, which is equal to 0. So in 2, what we do now is just to divide by cosine, assuming that cosine delta is different from 0. So that means that delta is a finite value, which also avoids being 0 here. And if we do that, we can reorder. So if we look at this equation here, what we get then is minus omega squared, and then sine delta divided by cosine delta is the same as tan delta, minus 2 gamma of omega tilde is equal to minus, and then I have tan delta. And now I can reorder the delta, the tan terms, and what I get then is that I get tan delta is equal to 2 gamma of omega tilde divided by 1 minus omega squared tilde. So what is going to come now, if you are not already saturated with trigonometric relations and manipulations, we're going to get a new applications of different relations of cosines and tan in order to simplify the equations. So at the end, we're actually going to get an analytical expression for this constant d. And that's always extremely useful when we want to compare a numerical approach with cases where we have analytical solutions. If you look at the mathematical pendulum, we are going to have a sine term in the, instead of x, which we have here, you're going to have a sine of an angle theta, then you will not be able to find analytical solutions. Except, as it's always shown in physics text, if you have an angle which is close to 0, because then you can replace sine theta with theta. And then you're back to this simple case which we have here. Well, not exactly simple, but it's a case where we have harmonic oscillator potential and a spring constant, which is an approximation to the problem. Okay, so let's continue with some further manipulations. I actually like this manipulation, so I really, when I took a course in mechanics, this was one of the parts which I really liked. So we remember also that sine delta squared plus cosine delta squared equal to 1. So this is just an exercise in using trigonometric relations. And then we have a tan squared of delta plus 1. That's given by a cosec delta squared. And the cosec is just cosine delta divided by sine delta. And we know that sine delta is given by a tan delta divided by tan squared delta minus 1. So what we're going to do now is actually to take tan delta given by this expression here and replace sine delta with this one. So if we do that, we are going to get, and we'll also use another relation here, we need a cosine. So we have a cosine squared of delta, which is equal to 1 minus, and then we have a sine squared delta. So what we get now when we use these relations, we get a sine delta, which is simply given by, if I now insert the expression for tan delta, so I'm going to use this expression here in terms of the frequency and plug that in here. When I then manipulate everything, what I'm going to get then is 2 times gamma of omega tilde squared divided by, and then I have 4 times gamma squared omega tilde squared plus 1 minus, and now I have gamma omega tilde squared and then squared again. And then I can rewrite everything and obtain a cosine delta. So I have also a cosine delta, which is going to be given cosine delta, which is now going to be given by 1 minus omega squared, and then divided by the same denominator which we had for the cosine term. So this same denominator here. Now I can actually insert this back into the equation for cosine. So the expression for D. So if you look at the expressions which we have, after we've done all these kind of manipulations, what I'm going to do now is to insert everything back into equation 1. So I have the cosine deltas, I have the sine deltas, F0 tilde is known, I have the cosine delta, and now I can find the term D. Yeah? Yeah. Let me just scroll down. Just say stop then, eh? Yeah. A little bit up. Yeah. You think about the cosine square? This one, right? This one? This one? That one? Oh yeah, but then I'm just plugging in the sine and the deltas. So if you look at this expression here for tan squared, what I'm doing then is that now I want to plug in the expressions which I have for tan squared, which is given by, sorry, this term here. Oh, that one, tan squared, yeah. This is cosine delta divided by sine delta. No, because now I have tan squared minus 1. You see that? I have this relation here. I think this is a cosine delta divided by sine delta squared, isn't it? I have to look it up there. Let's look it up after the break. Is that okay? But actually, I'm actually not using this expression. What I'm using is the expression here, which I plug in here. Yeah, let me just check it after the break here, if I've forgotten my trigonometry. So what I'm going to do now is to plug in these expressions for cosine delta, sine delta into this expression here. So insert in 1, and then we get an expression for d, which is going to be equal to f when we put everything together. And I hope I've done the math correctly here. So I'm going to get this denominator, which goes like 1 minus omega tilde squared and squared plus 4 times omega squared tilde multiplied with this damping factor gamma squared. And I can show that this delta, which is inverse tan, is then given by 2 times gamma of omega tilde divided by 1 minus omega tilde squared. So then I have an analytical answer, because the final solution, this x, this particular solution of x of tau, is given by this constant d times cosine of omega tilde tau minus this delta. So this was the formalism part. And now what we are ready to do now, when we have the equation, we can now look at the analysis of what this actually means. So the next part is actually to analyze. So this is the analysis which we are going to make of this particular equation here. So the term which is interesting for us now is what is called the amplitude. So this term d is actually the one which tells us how big the oscillation will be. So d is the one which now depends sensitively on the natural frequency of the system, the applied frequency of the external force, and this damping parameter gamma. So based on these parameters, which define the physical system, we can say something about how big the oscillation will be. So if we have a very weak external probe, then clearly the oscillation due to the force will be weak. And we are going to see that kind of analysis when we now look at the term d. So d is the term which we're going to look at. And clearly the cosine term is a term which gives us only the oscillations. So that doesn't, in a way, it doesn't give us so much interesting information. The interesting information is actually in the term d. And you can actually tune the frequency so you can get less damping or more damping. So let's take a look at it. And we can actually make some simple physics analysis based on this applied external force. So if we look at it, let's now go back a little bit and ask ourselves about the possible values which it can take. So let's just square the equation. So we just square d, so that we have f squared tilde divided by 1 minus omega squared plus this 4 times omega squared times gamma squared. And what is common to do now is actually to introduce, and if you go into different textbooks, you will often see that people introduce something which is called a damping constant. So we have defined this parameter gamma in terms of B, which is a kind of friction term or air resistance term, which depends on the specific velocity the system has. And it was divided by the mass and the natural frequency of the system. So what is common to introduce is a parameter beta, which is called a damping constant. And we will see why this becomes or can be interpreted as a damping constant. So we know that this parameter B is something which is related to the way the system is being damped. and we would write this as B divided by 2 divided by M here. So what we are going to do next is also to remind ourselves that this F squared of tilde is now given by the original amplitude of the force squared divided by the mass squared divided by the natural frequency cube, now 4 to the power of 4. So I'm going to define, to rewrite the equation for this D squared. And I'm going to rewrite this one as a parameter F squared divided by omega to the power of 4, omega 0 to the power of 4. So when I plug that in, I can rewrite my D as an F squared, which now depends only on the amplitude of the external force divided by the mass of the object we are looking at. And if I do that, I can rewrite this equation and just remind you that this omega tilde is the same as the original frequency divided by the natural frequency. So when I plug in this expression for F0 tilde, I can actually rewrite everything in terms of omega squared minus omega 0 squared, and this is squared again, plus 4 times this parameter beta and multiplied with omega squared here. So this is just a simple rewrite of the equations here. And the question which we are normally asked then is what happens when these constants take specific values? So a normal case is that this parameter beta is small. Beta is small because we are dividing with the friction dependent constant with the mass of the object, and it's a normal assumption in most actual cases it's a small parameter. Then what happens is that depending on the value of omega 0 and omega, we can get a value of D which can then look like this. So let's make a plot of it. And there are two situations which we can look at. So we can have one, vary omega 0. So you could now think of us varying omega 0 here, and you will see that this resonance would then peak around a given value of omega. And you can see that from the denominator here, that if the denominator is small, which means then when omega is equal to omega 0, what happens then is that you get just 1 divided by something which is small, beta 0 squared. And that means that this result will actually peak then. This is normally called a resonance in physics. And you can vary W0, which means the same as what you would be doing then is if you have a radio and you want to tune in a given channel, and actually nobody does that anymore. Nobody's tuning in a radio. This is something which I did as a kid. But this is a typical case where you can change the parameter. But the most common thing which we would do is actually to tune W. That's the standard approach. So you have an external force which apply to the system, and then you can tune the frequency of the force to get what's called a resonance or not. So that means that when the applied force has a frequency which is getting close to the natural frequency, that is when we can get this peak of the extension of the motion x. So remember now that x is proportional to this parameter d. So the larger d, the larger the swings in the motion. Okay, does that sound reasonable? So this is just a kind of physics analysis we can make with this particular solution. And the assumption now is that the particular solution is the one which is dominating after some time. And you saw that before spring break, and when we're going to rerun the calculations, you will see that the external force takes over, and then everything is forgotten about the initial conditions. And that means that damping and everything is just forgotten, and the external force is the one which makes the system oscillate back and forth in a very boring way. Normally. Okay, so this is the one typical situation, but the most common situation is actually to vary the parameter W. And that means that we would see something like this. So we change W, and then at the natural frequency, what we will get then is something which peaks here. So this is the value of D. And what we can do now is actually to find the maximum when the maximum occurs. When does the max value D occur? And that occurs obviously since this F, which we have in the denominator, is a constant. It means that when the numerator has just a constant, and the denominator, when that one peaks, when that one is at its smallest value, that is when D will have the largest value. So that means that the maximum D, that typically occurs when? So this occurs actually when we have D of D omega, when that reaches its maximum value. No, sorry, minimum value. I'm just mixing minima and maxima here. Squared plus this 4 times beta squared of omega. And we take the derivative and want to find when that is 0. And that gives us minus 4 times omega multiplied with omega 0 squared minus omega. And then I have plus 8 times beta squared multiplied with omega is equal to 0. We are obviously assuming that omega is different from 0. And so we can then divide by omega on both sides of the equations. And what we get then is an equation which runs like omega, we divide by 4. So we have a factor of 2 in front of the other equation. So we get an omega 0. So we divide by omega on both sides. So we get a plus an omega squared plus a 2 times beta squared. And this is equal to 0, which means that omega squared is equal to omega squared minus 2 times beta squared. And omega is then equal to, since this is a positive quantity, the frequency is a positive quantity, is then given by omega squared minus 2 beta squared. So when this damping factor is very small, when beta is much, much smaller than omega, then the difference, what we have then, the difference between omega and omega 0 is small. So we get omega squared. Sorry, not omega squared, but omega, which means in turn that we actually will be in a position where, if we look back at the denominator here, it means that the term which you see here will be close to 0. And the only term which survives is this one. Now we have assumed that beta is small. And since beta is small, then D squared is going to be small, it's large, since beta is small. But it depends obviously on the value of omega here. But we are going to have a small number multiplied with an omega. And that means that this is the case when D will start peaking. So for a specific omega 0 or omega close to omega 0, then the resonance for this D value will peak. And what happens then is that we have a maximum value. So if this is the case, that means that D max is going to be almost proportional, because omega is not necessarily equal to omega 0, but it will be given now by this term F0, as we called it, divided by 2 times beta multiplied with this W0. And the smaller the damping, the larger the response. And you can see that quickly now if you make a plot here. So we have now omega, and omega is close to omega 0. And if you now pick a specific value, so this is very schematic. So we would have a beta, which is equal to 0.1 times omega 0. And then if I increase it, or if I make it a little bit, well, you can see that my drawing skills are not optimal. So hopefully you can accept the quality of my drawing skills and just see the essential features of what you're getting now. So you have a beta equal 0.3 times omega 0, etc. So as the beta decreases, then this D peaks, and we call this for a resonance. And the peak gets higher and higher and sharper and sharper. So as beta decreases, then the resonance, that means this top, which we see here, this resonance peak gets sharper and sharper and higher and higher. Gets higher and sharper. So there are many ways of looking at this, and the thing now is that you can actually tune in many objects and cars, for instance. You can actually tune this damping constant and the frequency so that you can actually reduce this maximum large values for X. The sharpness of the peak is indicated by the ratio of its width, of this value of the width, which is now dominated by this parameter beta, to the position of W0. So if you want a very sharp resonance, it's actually common in the literature normally to introduce what is called a quality factor. And you can then rewrite the differential equation in terms of that. We will say a little bit more about that when we get back on Wednesday. But now I just wanted to give you the mathematical equations which are needed in order to make the kind of interpretations which we put up here. So I'm going to end by going back to the solution of the differential equations, which we discussed before spring break. And after this analytical exercises, when you now look at the numerics, which we end up setting up, this is much simpler. And the only thing which we need to do, and this is now related to homework number 6, the next homework. So you could actually take this code, or you could take the code which you have from the midterm, because we are still in a one-dimensional system. And you can see now the only thing you need to set up is the final time, the time steps you do, the initial conditions, you need always to specify those. And here in that code, which you find in the lecture notes, you will see that I have put a value for this gamma, 0.2. And then I have a frequency, which is now representing the ratio between the applied frequency divided by the natural frequency of the system. So it's put equal to 1. So that means that the natural frequency is actually equal to the applied frequency. And then I have a parameter for this F, which I just put to 1 here. And when you run this simulation, the only thing you need to do now is to set up the acceleration, which is given by this gamma multiplied with this V, and then you have an F tilde times a cosine multiplied with this omega tilde here. And here I'm using this Euler-Kromer method, where the only thing I do is to use the velocity, the updated velocity, to calculate the position. And typically what you would see is something like this, where now the way it swings, because I have a very large, or the value of X is going to have a large amplitude, because I put the applied frequency equal to the natural frequency of the system. So that means it's going to swing a lot between the two extremal values. So this is X, the position as a function of time. So if I now reduce that value, and we are going to look at the similar graph, you will see now that the extreme values of the position will be smaller, because we are getting away from the point where we have a resonance. So in this case, I put the driving frequency equal to the natural frequency of the system. And then I have extreme values which swing a lot. But what you also see is that after the initial conditions are suppressed, what takes over is actually the driving force. And now I'm just going to run one more small examples and then we stop today. So if I now change this one, so I make this driving frequency smaller than than the natural frequency of the system. And in this specific case, in the previous case, it would swing between minus 2.5 and 2. And now it swings only between minus 1.5 and 1.5. So here you see what happens when you have an applied frequency, which is different by a factor of 2 with respect to the natural frequency of the system. So you can really see in simple numerical simulation what you would expect based on your analytical analysis. So this is the kind of things which we will try to wrap up on Wednesday. And on Wednesday, I'm also going to show you how you can use something which is called Fourier theorem to actually generalize this to many other types of applied external forces. And that's an extremely powerful theory, which you will encounter in later physics courses. But now we're going to stop here today. And feel free to ask questions if things aren't clear. This today was a little bit more formalism and analysis, but I hope it was useful.